what we just talked about, because this is the big idea, the summation of the areas of rectangles. We have n of those, and we let n go to infinity. But what's that got to do with integration? And integration involves, we think of as involving that symbol. And when we use that symbol in section 5.1, we were finding what we call indefinite integrals. And when we use that symbol, we know that what's inside the parentheses is a what? A derivative, okay? And then on the end of this, we have to say dx, because that identifies the variable, our input variable of the derivative. But when we solved those problems, we ended up with what? Yeah, and we called that a what? If this is the derivative, we end up with the function which we call the antiderivative. Okay? So we have these pieces, section 1, 5.1, section 5.2. We looked a little bit at this in section 5.3, but now we come to the most important section of all, 5.4. And it's the fundamental theorem of calculus. How do we merge? What do we do? How does this area under the curve, by summing up infinitely many rectangle areas, connect with the indefinite integral? Any connection? I know you're thinking. I can see those minds churning. Let's see what we got. Function is continuous in the closed interval. The capital F is an antiderivative. Then what? What does that say to us? There's actually something missing. I think I need to add a little bit more. I need to put another equals out here. What would I say is equal to this is equal to that we've talked about already today? James, did you have an answer? Looked like you were formulating one there. Here?
No.
Okay, so this is not an equation, but this whole thing here. This is the limit definition of, in other words, if you don't want to do this work, you got to do this work. This is the limit definition of this definite integral. This is how we find the area under the curve. This is also how we find the area under the curve. So this whole thing here needs to go right there. Okay? They're all equal. So you don't want to go through and do the limit definition, the limit of the summation of the areas of those infinitely many rectangles. You don't want to have to go through that. That's a lot of work, just like it was with the limit definition of a derivative. So instead, we can write this notation. But again, this notation can mean nothing to us if we don't have understanding behind it. So how do I take all of this, use this notation to express the same thing, but what am I having, what's my process? What are my steps? What do I need to do? All I need is someone to just talk us through it. Okay. Find the antiderivative. Okay, and then Molly, go ahead. Upper bound. Okay, of the closed interval. Okay, plop that in the antiderivative. Subtract from it the antiderivative with the input of the lower bound. That gives you the area under the curve. That's the exact same thing. That's what we were talking about on Tuesday. It's the same thing, kind of like ragu spaghetti sauce. You don't have that commercial on TV anymore. You don't remember it, but it was the key line for that. It's the same thing. All those ingredients, same thing, okay? So you don't have to go through the limit of the summation of infinitely many rectangle areas. We can find the antiderivative of the function and then just use the upper and lower bounds. It's a moment of cheering. It's a moment of saying yay because it saves us a lot of work. Okay, now we did that. We looked at a couple of examples, as you recall. We did that example. Now, it doesn't mean that we don't have a lot of work to do. We still do. But it does mean that we don't have as much work to do. As much as this looks like, it still isn't as much as we would have otherwise. So let's do one more example. Remember, we're in section 5.4. As far as the book knows, we don't know integration by substitution. And I will be kind to you. If it needs integration by substitution, I'll tell you that, okay? So you won't have to guess. And if it's not integration by substitution, then you can assume it's simple integration. And if it's integration by substitution, I'll give you a hint on that. So we're not going to worry about trying to, let u equal and look at a composite function. Instead, we will look at this, integrating from 1 to 5, and we'll just build, two fractions out of this. 1 plus, I'm going to make this x to the negative 1, dx. Now, right now, do you have a visual about what you're going to be seeing if I ask you to graph this? Do you have a visual in your head? If I ask you to graph this, you're going to have an area from what to what? On which variable? The input. Okay, so 1, 2, 3, 4, 5. Okay, so I'm only interested in the area of the curve. What curve? I asked you to show this on graphically. What curve are you going to put in the calculator? F1 of x is going to be what? Okay. Some days I feel that way too. So we'll just do a quick little poll here. And everyone can participate, and if you don't feel like out loud, it's okay. Okay, everyone can participate now. We'll go back to the problem. The reason I'm asking this is that Tuesday, some people stumbled over a similar type of question. I want to make sure we understand it today. Four more people to participate here. Okay, I'm going to stop this pretty soon so you can put your answers in so I can save it to the portfolio as your participation grade for today. We have one more person. I think Kim's still pushing buttons there. Okay, let's see what we've got. Okay, very good. Very good. Okay. Do we see anything that's different from what everyone else has here? A little slightly different, and the Inspire doesn't know that, you know, for instance, this one is the same as that one, so I think everyone's got that. Very good. We'll stop that, save it to portfolio, now that I know everyone is with me today. So if we graph that, we put that in the Inspire, we're going to have then two vertical lines. We're going to be bounded by that curve and those two vertical lines. The first thing we have to do, find the antiderivative. Do you have it done already? If not, go ahead and work on that. What's the antiderivative? Help me out here. What's the rest of this? X plus, because this would be x to the 0 power. And I add 1 and divide by the new exponent. What's going to happen here? Again? Yep, natural log of x. Absolutely. If you forgot that, go back and make sure that you've got that. Now, how do I indicate that I'm going to only look at inputs from 1 to 5? I'll make sure you put it in parentheses. That bar is what we use from 1 to 5. This is otherwise known as f of x, or the antiderivative from 1 to 5. It's another way of writing that. According to the fundamental theorem of calculus, I take the antiderivative and I first insert what? The upper or lower bound? Upper bound, okay, minus the lower bound. And let's see, that's going to be 5 plus the natural log of 5 minus 1 plus the natural log of 1. What happened to the c that we always put in the antiderivative? It always cancels out because you're subtracting here. So our answer appears to be 4 plus the natural log of 5 minus the natural log of 1. But what do you know about the natural log of 1? It's 1? Okay, let's just check that out. Natural log of 1 has some value. Okay, that's an exponent on what base? This is the exponent on what base? What's the base of the natural log? E. Okay, e to what power is 1? 0. Okay, so this just cancels out to be 0, so our answer is 4 plus the natural log of 5. That would mean then that if we graph this and bound it by these vertical lines, the area would be 4 plus the natural log of 5. Let's check it out and see. So I'm going to go in here. I'm going to put in my fraction. I'm only interested between 1 and 5. Change the window. So I'm going to put in -1 to 6, scale by 1. And I saw the graph before I started this. There's nothing that's in the negative, you know, in the below the input axis. So I think I'll put in -1 and go up to 6 again. Looked like that was pretty good. And scale by 1. And I want to integrate from 1 to 5. Now again, to do this, you have to use the analyze graph piece. And if we use the analyze graph piece, you pick up what looks to be, oops, let's try that again. Analyze graph piece. There we go. And we want to go over to 5. And what did I have my input? I forget now. Looks like almost 6, so I'm going to put it right there. My answer